In this video, I'll be touching on certain concepts of force and momentum that most of you still find difficult. Okay, in question 7, I received feedback saying that the free body diagram for these particular situations is quite different from other situations. Okay, so in question 7, we are given the information that the climber is taking a rest. And from this picture, which is a simplified version, it seems like this person is floating in the air. Okay, and then in the questions, we were given again that, these situations is actually supported by friction force. Okay, so what it means is that his weight is being supported by friction force. And then this friction force is produced by his shoes and his back. Okay, so in these situations, it is a bit hard to imagine where does this friction force comes from. So I would like to divert you to another situations, which is actually very similar to this one. Okay, so imagine we have these two cases, okay, whereby in both cases we have a sponge that is being pushed from the top to the bottom, right? And while being pushed, this sponge in the first case stuck in between two glasses. All right, and in another scenario here, we have sponge being pushed from the top to the bottom, also having glass in between. And in these situations, however, these two glasses is more further apart compared to our first situation here. Now, which situation you think the sponge will be harder to push? I believe most of you will choose this scenario, right? This scenario, the sponge is harder to be pushed by the force. Why? Harder to be pushed. Why? Easier to be pushed. Why? Okay, so in the first situation, it is harder to be pushed because you will feel like there are frictions, right? And with sponge, it's easier to imagine because the sponge comes into contact with this glass as you push from the top, right? And then when it comes to contact with glass, what happened? Okay, so when it comes into contact with glass, right, it tries to push the glass away as you push from the top, right? And there is another force that is produced by this F, okay, which is produced from the wall, right? So this normal force, according to Professor Richard Watson's, in his book University Physics, the magnitude of frictional force depends on depends on magnitude of normal force, okay, acting between surface and the body contact, the contact of body. So which is why this situation you will feel that there is a friction force that goes against the force pushing it down, right? Because this friction is a result of the normal force produced when the sponge is pushing against the glasses, okay? And while the other one, the sponge is not pushing the glasses, so you feel like it's frictionless. Nothing is going against the F. So back to our original situation here. So don't you think this person is like that sponge that we try to push down? And that there is a friction force that goes against the weight, right? Again, this friction force is produced by the normal force from the shoes, which the normal was produced by the force that the shoes exerted on the wall. And at the same time, the friction force is contributed by the normal force produced from the body, whereby his back is exerted a force against a wall, right? So in this case, our free body diagram will be weight and friction force from the shoes and friction force from the back, and the force that actually being pushed on the wall from the shoes and from the back. So that is how our free body diagram is constructed. Okay, as for question 12 and 13, many of you find them difficult. I think it's because you didn't start off with a good diagram. Okay, so as you can see, I outlined the free body diagram of both questions. And if you notice, it looked quite similar. Okay, you just have to get the diagram right. Make sure the angle that you show here is clearly written, okay, and clearly shown, so that you can break down each of these force into its own horizontal component and vertical component. All right, because that's what matters. Okay, I noticed in the breakout rooms, several students mentioned question 10 is a bit complicated. Okay, I would like to clarify here. The difficulty could arise because you are confused by the direction of the velocity. Yeah. So in question 10, what happened is I draw a picture of the story actually. So in question 10, you have a rocket at first traveling at velocity 45 meter per second in horizontal direction, yeah, in I direction. And after some time, probably there's a explosion or something, it break into two pieces. Okay, so when it break into two pieces, so one piece actually travels 30 degree above the ground, and I mean the 30 degrees from the x-axis lah, from the original directions. Okay, so the deviation is 30 degree above the line, and the other component is traveling at another direction 60 degree below x-axis. So these two directions. Okay, don't get confused by the direction, because in this phenomena, conservation of momentum still applies anyhow. Okay, you have one object that breaks into two. Okay, so how do you write that conservation of momentum? Okay, anyway, so in this case, you just have to break your calculations in two components. So first, you will calculate the horizontal component. Okay, just make things simple. Break into two components. So for horizontal component means we're going to do calculations based on the x-axis line here, this line. Okay, so in horizontal component, so initially the momentum is mux. Okay, and then after something happened, okay, the momentum has two parts. All right, so you have one contributed by the first mass, this mass. Okay, we don't know what's the mass, but we know it's half of the original mass, m, 0.5 m. And the velocity, we will just take the horizontal part of the velocity because that's what we are interested with, horizontal. Okay, and for the other mass, we will have also its own mass, m2, but in this case, we use 0.5 m because we know it's half of the original mass of the rocket. And the velocity, we are only interested with the horizontal component. Okay, so I think by now you know how this cos 60 come by and how this cos 30 come by lah. Okay, so from here you just simplify and obtain the first equations, right? Don't worry about the v1 and v2. Okay, and for vertical component, right now we are interested with the other part of the component, and initially there is no vertical component, we only have horizontal. Okay, so just use conservation of momentum equations, right? Initially no vertical component, but after the explosion or whatever it happens, we have vertical component introduced in the system. Okay, and you will notice that v1 sine 30 is positive and the other one is negative, because in the system you notice the vertical component for this v2 is actually going downwards, so there is a negative component in these equations for velocity part. And just simplify as you can and try to retain as many decimal places as possible. Okay, and you have the second equations and just do the substitutions, and you'll notice that v2 is 45. Okay, and then v1 is just the product of 1.732 from the second equations, okay, with the v2, and you get 77.94 meter per second. Okay, in question 11, the system involves a person pushing a barrier upwards an inclined plane, which looks something like this. Okay, so the inclined plane is 35 degree, okay, above the ground. Okay, and the barrel okay, is pushed as far as 3 meter, okay, by a person, right? The force that he exerted is in a horizontal direction, right? And this is 35 degree. Okay, that's the force, and this force is 120 Newton or 120 I. Okay, so in question 11 you are asked to determine the acceleration of the barrel, and so before that you have to draw the free body diagram, and most of you are able to construct that free body diagram, no problem. Okay, so for this question I'll just be talking about the work done in this situation. Okay, now work done, all of you know that it is actually a dot product of two vector. This dot product, knowing that this is a dot product is very important. So it's a dot product of two vector. First vector will be vector force, okay, and the other vector will be displacement. Alright, so knowing these two is very important. So if you want to calculate work done by this force F, then this vector force will be 120I. Okay, now if you are calculating work done by gravitational force, okay, or rather by the weight, then you have to put in the weight vector and dot with the displacement vector. Okay, so in this case, this is our displacement vector S. Okay, S, and this has some angle above the ground. Okay, and our weight vector is here. Okay, so we're going to take the dot product of these two vectors, but of course before that you need to know what is the vector. Okay, so you all know W will be mg, right? Mg, and it's negative mg in j direction, right? There's no I direction for W because there's no horizontal component. Okay, but for S there are two components, right? You all know by now that a vector consists of summation of two components. One is horizontal, one is vertical. Okay, horizontal will be this one, right? So what is Sx? Okay, by now you should know that this is actually magnitude of S and also cos 35, and this is magnitude of S sine 35, right? So in here, magnitude of S is 3 in this case, so it is 3 cos 35I plus 3 sine 35J. Okay, so how do we do dot product in this case? Okay, it is very similar to the normal multiplication. All right, so you just multiply this to 3 cos 35 and negative mg to 3 sine 35. Okay, however, I dot with j is 0. Okay, I dot with j is equal to 0. Okay, that's therefore we only left with the j dot j. Okay, j dot j is 1. Okay, so at the end you have negative mg 3 sine 35. J dot j is 1, so you can skip that. So at the end you can get your final answer here just by substituting your m and your g. This is one of the picture I took when I was in a temple in Thailand, and you can notice that it is pretty similar to the cover page, but a different perspective. Just want to show you that when you change your viewing angle, the world will look differently. I wish you all the best in your future studies. Ouch, there's one thing that I forgot to share almost. I want to demonstrate an example of how to explain a solution in an efficient, concise, and a clear manner.
Muhammad Nazim Ruzaini. Is he here?
Yes, 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 yes.
Yeah. Elastic acting for 9A.
So we'll use the formula which is M1 U1 plus M2 U2 equals to M1 V1 plus M2 V2. So we substitute every every information that has been given, which is M1 is the mass of the truck, which is 1,800 kilogram. U1 is the initial velocity for the truck, which is 20 meter per second. M2 is for the car, which is 850 kilogram. Then just substitute and uh, calculate it, and you'll get the V1, which is velocity for the final velocity for the truck, which is 14.33 meter per second. Did you get it?
Yes. Anyone have problems with question 9A? Everyone okay with it?
Yeah.
Yeah, okay.
Yeah.
Yeah.
You
So can you proceed to the B?
yes, you can proceed to 9B.
So the difference between question A and B is question A state that the car initially at rest, but for the B question state that the car initially moving with velocity 12 meter per second. So we just we still using the same formula because the both of vehicles separate after impact, which mean we still use the M1 U1 plus M2 U2 equals to M1 V1 plus M2 V2, and we just change the value of U2 equals to 12 and V2 equals to 16. So when you calculate it, and you get V1 is 18.1 meter per second.
Okay.
Okay, for the last
Okay.
question for number 9 is the initial velocity of the car is 12 meter per second in the same direction as the truck, and the two vehicles stick together after impact. So the keyword of this question is the both of vehicles stick together after impact. So this means the velocity of the final velocity will be the same for the both vehicle. So we use the different formula, which is M1 U1 plus M2 U2 equals to M plus M1 plus M2 times by V, which is both of the vehicle have the same velocity. So when we substitute in the equation, and we'll get V is 17.43 meter per second.
Okay. So everyone clear again? Is it okay with the explanation from Nazim? Okay.
Okay.
Okay. Okay. Thank you.